Hi, I'm going to talk about the SAGE model in natural language processing, which is the abbreviation of the sparse additive generative models of text. So prior to this, the introduction of this SAGE model, the generative models of text typically associated with the Dirichlet multinomial generative model, which is exploiting the conjugacy between the Dirichlet distribution and the multinomial distribution. Because so just as a brief introduction of these two distributions, you could think of as the multinomial distribution as a generalization of the binomial distribution. So it's basically the distribution of multiple choices, like K outcomes, for multiple experiments. And the Dirichlet distribution which is the generalization of the beta distribution, is now the probabilities of the multiple weights, because as we know, the beta distribution is probability of probability, which is for two outcomes, probability of success or not. But now the Dirichlet distribution is a generalization, so there's a weight vector of probability 0.3, 0.2, 0.5, something like that. And yeah, so what does it mean to exploit the conjugacy between these two distributions is in terms of the Bayesian theorem. So when the posterior distribution, which we want to know but is intractable, so we in the Naive theorem, we are going to utilize our prior knowledge, our belief in terms of the prior distribution. And also based on the prior belief, we could calculate the likelihood, right? So by using the two factors, like we're not going to talk about the normalization term, which is in the denominator, because it's not needed. So yeah, so why conjugacy is good? It's because if our prior distribution is the Dirichlet distribution, which then and our posterior, which we desire, is the same distribution, right? That's the definition of conjugacy. Then we can just calculate it by updating the parameter of the prior distribution. So in this case, we could just update the concentration parameter alpha of the Dirichlet distribution based on the multinomial, the likelihood, to arrive to our posterior distribution estimate. Okay. So yeah, this sounds like a fair approach, which is also very effective. So what would be the limitations from this approach? The first approach that this publication addresses is that when it comes to when we combine with multiple generative variables facets, especially when those variables are latent, which means that it's unobserved, then with this approach, we would have to, for each token, each word, we would have to use a switch variable to control which latent facet is currently alive. For example, yeah, this term facet could be a little bit confusing, but it could be like a topic or perspective, as you can see in the diagram in the left bottom. Yeah, so each topic and perspective is an example of a facet in this case. So okay, so in terms of the diagram, to explain it, so in the word distribution diagram here, each bar corresponds to a word's distribution, raw probability. So basically, we're trying to figure out which one of these background or topic or perspective is responsible for that specific distribution of that specific word. So we're basically, you can think of as copying one bar from the left among these three, choose one, and through the switch variable, we now, like for example, let's say that we want to figure out the distribution of the word A. Okay, now for that word A, we determine for word A is topic facet responsible, perspective facet responsible. We determine that and then copy and paste that bar, which is the word distribution for that particular A over here. So as you can see, so this means that like not even like we would also need some additional latent variables because the topic is not only comprised of one topic, is a facet. It could be topic 1, topic 2. So we would need additional latent variables to account for that. And also it would be because words would not only, it could also be the case that they are their distribution should be determined by a combination of topic 1 and perspective 2. In that case, the latent number of latent variables will explode as the number of combinations between the unique topics and the unique perspectives. So that basically increases the inference cost exponentially, which means that we would want to come up with a different, more clever way. And also one more thing is that, so because there's so much weight, so much stuff to learn here, right? The bars are no bar is 0, which is basically, so we're not dealing with some sparse measures, right? Which is desirable in learning because sparsity could control could prevent us from overfitting. And yeah, so in terms of sparsity, it is possible to forcefully induce zeros in these multinomials, right? Because we could just manipulate the Dirichlet prior, right? Because let's say that the Dirichlet prior is, let's say that is a vector. One of the instance is a vector of 3, length 3. Then so in that vector, then the first element would account for topic 1, the second topic 2, third topic 3, right? So we have a bunch of those, which makes the Dirichlet distribution the probability of those vectors, a lot of those kind of vectors. So a lot of them would have so some of them would have 0 for topic 1, like completely 0. Some of the weights obviously would, right? Then we could manipulate the concentration parameter so that the probability density for that weight is very high, which is basically equivalent to inducing zeros forcefully. But that kind of sparsity is illogical, which will, because we're just imposing it, so will not make the model stable at all. So yeah, so naturally this approach doesn't really have such sparsity advantages. Okay. Yeah, to just sum up, the root cause for the Dirichlet multinomial generation model is that we're trying to directly model the word probabilities associated with each document class or latent factor. We're trying to get the 1-by-1 correspondence there, which the number of cases would explode again. So what would be the alternative? The alternative is of course the SAGE model. So why is it called the sparse additive generative model? Okay, so first of all, yeah, okay, to dissect this term, sparse additive, the generative model is just term, right? Sparse comes from the fact that we are modeling each facet, like for example, topic or perspective, those kind of metadata, so on, right? We are modeling each facet sparse, 0 mean deviations in terms of log frequencies from the background word log frequency. Now we are no longer dealing with the raw probabilities in terms of the word distribution. Now we're dealing with frequencies, which makes it additive, right? So which means that instead of we have to use some switch variable to make a one-to-one correspondence between some kind of bar and some kind of bar in the destination. We don't have to do that, but we can just add the log frequencies across the background distribution, facet 1, which is topic here, facet 2, perspective here. But also we could sparse his zero mean. We could control that as zero mean because first of all, there are deviations, and sparsity, as we discussed, has an effect of controlling for overfitting. Yeah, so that's the idea. Okay, so yeah, so like just to give a concrete example, it would be like if you're trying to model a tweet on topic of COVID-19. The topic is COVID-19 for the tweet from a risk-averse perspective, okay? So that tweet might have just the frequency, right? We count it and just do the log on it, right? Log is for later, I'll explain. And then for that topic, which is facet 1, think about it, facet 1, it would have some kind of log frequency deviation from the background, right? For topic 1, for example, for this topic of COVID-19, a word called of grocery might have a stronger deviation from the background, right? It's possible, right? Because it's more meaningful for that topic of COVID-19. But some other words like just function words like the, or those kind of words will not really add any value to that topic, which we will not result in the some deviation from the background. So we can just control them as zero. Of course, there should be a threshold associated with it. Like for example, if the deviation is just this, the difference from the deviation is just this much, then just count it as zero, which makes this model sparse, which is desirable. Okay. Yeah, so yeah, the inference cost so can be very low. We no longer need the switch variable, right? Okay. Yeah, so yeah, let's dig into the Sage generative step, the generative story of this Sage model. Okay, yeah, so first of all, I would like to go over some, I wouldn't have to go. Okay, so now the natural language process models are still there. Like for example, naive Bayes classifier, naive Bayes classification model, right? Which is a very standard text mining algorithm. And it uses the standard multinomial, right? It uses the standard multinomial in the standard naive Bayes classifier approach. But now we are switching that standard multinomial component in naive Bayes classifier with this Sage model. So it's a drop-in replacement of Sage model, okay? So which implies, so that's the point. And okay, to just again emphasize, this Sage model's main advantage is that we can we can use a sparsity inducing priors. Okay, sparsity leads to control of overfitting, which is equivalent to the model's robustness. Okay, so that's what to remember. So then, how do we obtain this robustness by sparsity? So now we are going to use as a prior probability distribution, we are going to use the zero mean Laplace distribution. Okay, so and with the zero mean Laplace distribution, okay, so there's an identity relationship between the Laplace distribution and the compound of the normal distribution and the exponential distribution. We're going to utilize this identity. And why do we need this Laplace distribution? And the reason is because it has the same effect as placing an L1 regularizer on each term in component, okay? Which L1 regularizer is the L1 that we know from L1, L2 elastic net. So it's basically controlling, it's basically setting a lot of weights as zero, which is which is basically same as inducing sparsity, which we discussed. But so that sparsity specifically comes from, okay, Laplace distribution. We are going to have Laplace distribution has an identity with the compound of normal distribution, exponential distribution. The normal distribution now is going to have the mean of 0 for sparsity, which is sparsity is a lot of zeros, right? So the normal distribution mean will be 0, right? And the normal normal distribution's variance will be controlled by the exponential distribution. And that reason is also to permit extreme deviations from the mean by controlling the parameter of the exponential distribution, okay? So in that case, since we have to control the variance of the normal distribution, which is the exponential distribution, then we would have to obviously we would have to obviously treat that variance also as a latent variable, so we can fit on it. Yep. So here's a pseudocode for the generative story of Sage in the naive-Bayes classifier. It's pretty standard. So okay, so we draw the background M. This is the word distribution, like specifically the word log frequency. We draw it, and then for each class, now we're in the MB class. So each class is the component, right? The facet. And this is an naive-Bayes classifier problem, so it's here used as class. And for each class and for each term, we draw the variance from the exponential distribution, and based on that drawn variance, we draw the normal distribution. Now, as I said before, normal distribution mean should be set as 0 to account for sparsity, right? And then based on that facet, which is here, the class, right? Then we add the log frequency of this drawn facet class vector for the vector of weights for class K, and add it to the log frequency of the background log frequency, which is M here, right? And then since these are log, we exponentiated, which gives a nice weight, which is expressed as beta, the word distribution for that class K. And then now the second is the actual sampling part, generating part. For each document, we draw some class from a uniform distribution. Here might be the uniform distribution because now we really have no criteria to how to give weights to each class, right? So it's natural to think as it's a randomly drawing a class. Then based on that drawn random class, we generate words based on the word distribution, which was generated in the previous step. So okay, in the high level idea, we're just initiating parameters and generating the documents, which is done in the generative step of the generative model, machine learning. Okay, so now, yeah, so now we generated. So then, of course, we would want to estimate, right? Since we generated with some random, we just generated the tau here, the variance, and the eta, the component vector. We drew it. So now we would want them to be the right value because we just, yeah. So we were trying to converge to the right value, right? So which is the Sage estimation part. Yeah. So the estimation of the eta, which is the component, is is the component mean. The component is the component eta itself is composed of two parts, right? The component mean and the variance of that component, right? Which means that, but the component mean should be a point estimate instead of total posterior distribution because of this reason, okay? Because let's say that the expectation of the point estimate So basically, this is about the sparsity. Now, okay, the point, the component mean, even when the expectation of that component mean is 0, if we are dealing with the posterior probability distribution, which also includes the variance, despite the expectation of that component mean is 0, the variance will perturb that component bigger than 0 likely, right? So in that case, now we can't realize the sparsity because even though when the component mean is 0, a small kind of variance like 0.0555 will make will not make the error 0, but a little bit not exactly same as 0, which is desired for sparsity. It could lead to 0.0005, which is more close. You can think of it as it's more like an L2 regularization. Instead, we want L1 regularization, which is exact 0, not the L2, which is very close to 0, right? We don't want that. So we want to avoid that kind of case, which means that when you say the expectation of the component mean is 0, it's just 0, no variance factor at all, which means that, and to estimate that point estimate, we cannot do it. We cannot estimate with the Bayesian inference, which fully calculates the posterior probability distribution. That can be done by the maximum a posteriori, the MAP, right? We are using MAP instead of MLE, which is the maximum likelihood estimation, because we are combining with priors. That's the point. So yeah, so component mean with MAP that returns point estimate because we want sparsity in our model, right? And that's the component mean is the first part of the component itself, and the second part of the component is the variance, right? So the variance, we have no such sparsity constraint, so we can estimate it with the Bayesian inference, which fully calculates the posterior probability distribution. And the specific estimation method is the variational inference. Okay, so the objective of the variational inference is to approximate that. We don't know the true posterior probability distribution. We don't know the true posterior probability distribution, P here. We want to know that. We want to, but we can't just know that right away. It's intractable. So we would like to closely approximate to it, which we use by the variational distribution here as Q. Okay, so we want. So okay, so we know that the KL divergence is the metric that measures the proximity between the two true and approximate, those two probability distribution. KL divergence measures that. So we would want to minimize that KL divergence to make those two true and approximate distributions as close as possible. But the problem is that to calculate this KL divergence right away is intractable because the equation itself directly depends on the posterior distribution, which we want to know but can't right now. So it doesn't make sense that we can just get the KL divergence. So how to tackle this? We use a property of the log of marginal likelihood, PX, the model evidence, which, for example, in this case, the evidence would be the word distribution that we got, which is observed. We know it. Yeah, in our case. So the thing is that the KL divergence and this lower bound of the evidence, the model evidence, the marginal likelihood PX, the sum of these two, K divergence and the evidence lower bound, aka elbow, the sum of it is equal to the log of marginal likelihood, which the marginal likelihood is constant with respect to the variational parameter, which means that if the KO divergence between to its max, then the lower bound becomes 0. And if the lower bound hits its max, then the KO divergence becomes 0, right? So so in this case, the problem of minimizing the KO divergence is exactly equivalent to maximizing the evidence lower bound. And the advantage is that this evidence lower bound to calculate this evidence lower bound, we do not need the posterior distribution. So the calculation is no longer intractable. Okay. Yeah, so graphically you can think of, like, as you can see, there's when the elbow becomes max, the KO becomes 0, right? As you can see here. So we have to maximize the elbow, so it gets same as this log of marginal likelihood. Okay. And okay, so this elbow, this equation, expectation, when we rearrange the terms, when we expand the term, it's basically the elbow is equivalent to the energy subtracted by the entropy, as you can see here. And this equation relates to the lower bound that was given in this publication, which is, okay, so it's basically the energy here. This is basically the joint probability of the observed and the latent. X is observed in this case. In our case, is the word distribution that's observed, and Z is the latent variable. Okay, not necessarily latent variable in this case, but anyway, the variable that like, okay, in the ninth case, class variable could be the class label. In the extension of this model, which deals with actual latent variables, it will be that in that case. Okay, so yeah, so yeah, actually this Z would yeah, that makes sense. Okay, yeah, so it's basically subtraction of this joint probability subtracted by this estimation, right? Which is basically these two, the highest equation and the second equation, which L, the small l in the left-hand side of the equation, is the lower bound, denotes the lower bound, which is the same thing at elbow here. So the first in the right-hand side equation, the first, second, third term, this is basically the expansion of the joint probability distribution, right? Because it's in log terms, it's additive. So this first three terms in equation 2 correspond to the first term in equation, the highest equation here, the joint probability distribution, right? So you can see the correspondence, the second term to the last term. Yeah. Yeah. So yeah, we can see that. So yeah, our objective, to again remind, is to maximize this lower bound elbow, lower bound for stage. Maximizing this lower bound is equal to minimizing the KO divergence, which we couldn't calculate because it was intractable. But now it's tractable, and by maximizing, we could make the true posterior distribution, which we want to know, and our variational distribution the closest possible. So we are basically approximating it. Yes, and yeah, so it's, as I said before, again, it's in a two-step process. The component mean has to be done by getting the point estimate, which involves the maximum a posteriori, and the variance of the component does not have such sparsity constraints, so we can just do a Bayesian inference. So it's two parts in estimation. Okay. Yeah, so what kind of method in estimation are we using in terms of optimization? Okay. Yeah, first of all, for both two steps, we're using the Newton optimization, which is basically, yeah, it's a gradient optimization technique that involves with the gradient, but the Newton method is not the same as gradient descent because it also uses the second derivatives. So the Newton method uses both the first derivative, which is the gradient, and the second derivative, which is done by the Hessian metrics. So yeah, so to just do again say, the gradient, as we know, tells us the direction in which the objective function, in this case our lower bound, maximizes most quickly. So that's shown by the sign of the first derivative, whether we go up or whether we go down in that axis direction. And yeah, and the the scalar, the number for that, the derivative, the value would be the rate of increase in that direction. So that's the gradient part. So it's telling, it's kind of like directing which way to go. And so, and the, okay, so Newton's method difference from the gradient is that it utilizes a second derivative, which is done by the, which is with the Hessian matrix, right? And what does this imply in the higher level? It means that the Hessian matrix will tell the optimal step size to move that in the, to move in that direction, which was directed by the gradient. Okay, because usually in gradient descent algorithms, okay, so first of all, this computing this Hessian matrix is very, very expensive computationally. So in, for example, in neural networks, or which involve deep neural networks, those kind of areas is not used because it's too expensive computationally. So they, in their case, a lot of them just use some kind of a parameter that controls the step size, like alpha. But in this case, but that alpha, of course, people can decay it or just control, play with it. But anyway, it's the, by definition, those alpha is just a hyperparameter. It's not optimal by itself. But the second derivative here says the optimal step size, which means that it could avoid in converging, wrongly converging to some saddle points like local minimas, right? Saddle point, which is in some direction is the maximum, but in some direction is the minimum. So that's the tricky part. But this Hessian matrix could most likely avoid in going to those points, which is not the highest point or the lowest point in the descent algorithm. Yeah. So yeah. So in terms of equation, you can see that yeah, the equation 3 here is in the total, because we are dividing the lower bound into two parts, which the first part that accounts for the component mean, which is equation 3 here, and also also the component that account for the variance of the component, which we'll see in the next slide. Okay, so equation 3 is the relevant part of component mean in the lower bound. And equation 4 is the gradient, as I said. Which direction do we have to move? Okay. And the last, equation 5 here, as you can see, is a Hessian. You can see that it's Hessian, right? The first term here is doing second derivative with the same variable. And the second term is with different, right? You can see that this accounts for, this composes of the Hessian matrix, which tells us optimal step size in our, how much we will have to move in our, and which is optimal here in our optimization step. So the last equation now shows that, yeah, so now we're clearly both using it. We're the delta, the negative delta component here, component mean to be exact, is the update from Newton's method, which uses the second derivative Hessian here and the first derivative gradient here. Okay, so yeah, we talked about, so just before we talked about the component mean of the component. Now we're going to talk about the variance in the component. So the variance in the component, we don't have to stick to the point estimate, which is done by MAP. We have no sparsity constraint, so we can just do the Bayesian inference on the variance, which means that we are going to fully calculate the posterior distribution. Okay, and remember that the prior probability distribution, the prior on the variance, was based on the exponential distribution, as we said before, which is the second part of the compound of the second part of the compound mode of the normal distribution and exponential distribution, which is equivalent to the Laplace distribution for the, which gives the L1 regulation effect. So as you can see, this prior is in the, okay, to approximate this prior, to kind of to get closer to this prior, we choose the gamma distribution, which is also in the exponential family, right? And this gamma distribution has two parameters. which is the shape parameter and the scale parameter. And we know that the product of these two shape and scale parameters is equal to the mean. In this case, since our interest in the tau variance, the mean of this alpha and beta will be equal to this, the expectation of the variance here, the tau, okay? So this is just the PDF, probability density function of the gamma distribution, okay? Yeah, so basically we are constructing a fully factored variational distribution, which we want to be as close as the true probability distribution on the variance. Okay, so equation 7 here now is the relevant part to the variance of the component in the lower bound. So now we want to optimize this part, right? And again, the derivation is very dirty, but anyway, the point to take from here is that these last two equations are about the Newton optimization for each parameters for the gamma distribution. Gamma distribution parameters, the first one, shape parameter, expresses alpha here. We can also get as you can see here, we are also getting the update of that alpha, which is basically the product, which is basically got constructed equivalent to getting constructed by the first and second derivative, the Hessian and the gradient, right? Hessian matrix and the gradient, and the beta update is not even an update. It just is. We could just calculate it with a closed form. It's basically the closed form update. Okay, so in this case, the idea is that we are doing the same thing with another part. So so that was the estimation. Okay, that was the estimation for the naive Bayes classifier when SAGE model replaces the standard multinomial. Okay, that was the previous before we were talking about the MB classifier. Okay, so before talking about that, so before that our model had a hyperparameter, right? As we know, hyperparameter is a user-defined parameter that we have to choose. Of course, we could do the grid search, but like if we could find a way that we don't have to deal with defining the hyperparameter, then it would be better, right? So so the hyperparameter in our case was the rate parameter of the exponential distribution. There's a little bit of error in this slide, but basically the gamma over here. So, and instead of using that gamma, the rate parameter of the exponential distribution, which was used for the variance of the component, now we replace the prior for variance from exponential into the Jeffreys prior distribution, which is improper. And okay, so Jeffreys prior distribution is basically the inverse of the tau, which is the variance. So we initiate with tau. We initiate the tau vector, which is the variance vector for each components, and then the distribution of them, the PDF of them would just be the inverse value of those each variance for each term's component. Okay, so think of as tau as a huge vector which has the same length as the vector for the component mean. So it would be our elements, right, which would be initiated with some kind of some values. So we're basically just getting the inverse of those to construct the PDF of the prior of the variance Makes sense, right? And this is, so by doing this, in the higher level idea, we are no longer having this, we are no longer using the, okay, so previously, we want the L1 regularization effect from the Laplace distribution, which the Laplace distribution is the compound model of the normal distribution and the exponential distribution, which the priors of it, right? But now, instead, normal distribution is still there, okay? But the exponential distribution, because it involves a hyperparameter, which we don't want to deal with, because of that, we replace that exponential distribution with the Jeffreys prior distribution, which doesn't involve any hyperparameter, but we can just get the inverse of the tau, the variance for each term. Now we no longer have to deal with choosing the hyperparameter, okay? Which is, this is, so now, since now our model is a compound of the normal distribution and the Jeffreys distribution, that means that we no longer have the Laplace distribution anymore, which the Laplace distribution had this L1 regularization effect, right? So then wouldn't it be bad? Sure, it's Jeffreys prior distribution. Jeffreys distribution is an improper one, but empirically also has good results. So that's the point, okay? Yeah, so again, back to the subject. Yeah, so up to this point, we were talking about the case of substituting the SAGE model, the SAGE, to the conventional Dirichlet multinomial in the naive Bayes classifier, right? And by nature of the naive Bayes classifier, we are given a bunch of class labels, right? Based on that, we are trying to based on that, we are constructing the prior and the likelihood, and then we determine which this tweet should belong to class 1, class 2. So yeah, so the main point is that we are given the class label. In this case, the component facet is observed. We are given. Yeah. So which means that what I talked about is basically when the component is just given as granted. But this model extended to cases when one or more components are not observed, which are latent variables, which is actually more useful, because we want to know, we would like to, like, given a corpus, we would want to, like, of course, we would have, in that case, we would have to specify the number of topics, which is basically a very hard thing to do. But based on that, we would want to extract topics given a corpus. We want to know which subtexts documents are most closely related to each other, and like try to get the keyword of that clusters. We want to do that, which is dealing with latent components, latent topics, latent metadata, whatever. So in that case, yeah, we are going to estimate the latent components. And in this case, technically, the MAP estimation for the component mean slightly changes, okay? The equation, as you can see in the upper equation, which the lower bound, the relevant parts of the component mean add a subscript k to the lower bound L here, this equation. Now, in this place, where this distribution Q places, when the component was observed, in that place, there used to be this C, okay, which is a true count. But now, since the component we can't see is latent, unobservable, we cannot use the true count, but we have to estimate it. So we are going to use the expectation of the true count, which is basically based on the variational distribution here. CN subscript is for some, it's the index for the latent component. So based on the distribution, variational distribution of the latent variable, we're going to try to get the expectation of the true count, since we are no longer given the true count, since we're dealing with latent variables. Okay, so that's the change in the equation. And okay, so here, as we can see, the distribution of the generative model is now here. The first one, the upper one, is when there's one latent component, right? No longer observed. As you can see, there's the index, right? Z, and the distribution for the generative model in the beneath here is when there are more than one latent variable. Here specifically, as you can see, this term, the power of in the exponentiating function, exponent is that the first term, the eta to the subscript of Cn, this first term accounts for the topic. The second accounts for the perspective. For example, any metadata. It could be like the text, for example, for articles, which post, I mean, whether it's written by Fox or CNN, which perspective does it have? That could be an example of the component, right? Which is latent. That could be, considering that we don't know whether it's from CNN or I lost a little bit right here in terms of explanation. But anyway, the point is that all of these eras are latent. So latent, it could be latent topic, latent perspective. Latent perspective in true value, it could be whether it's written by CNN or Fox, or like there's categories, right? But we don't know if this is dealing with based on those CNN, Fox. We don't know. We're just trying to infer. So that could be one aspect, right? Perspective, the latent component. And the last third term is interaction between the topic, and it accounts for the possible interaction effect between the first and the second latent variables. And those are all, again, to emphasize, are added. These are all log frequencies, and all basically, though these are the sparse deviations from the baseline, the background log frequency, which the baseline log frequency is m here. And since frequency, we can do it additive, so we don't need switch variables as we did in the Dirichlet multinomial, which makes everybody happy, which is computationally better, and also you can combine multiple facets at once instead of trying to choose from either one. Okay, this is the plate diagram for this multifaceted topic model used in Sage. To just briefly explain this plate. At first, this alpha is the concentration parameter for the Dirichlet distribution. Based on that distribution, the weights are, there will be a bunch of weights, right? Weights will be based on the probability, based on the density of that Dirichlet distribution. We could obtain a weight factor, right? Because the Dirichlet distribution is basically the probabilities of those weights, which are weights accounting for multiple choices in many experiments, right? Not only one, but many, okay? So based on that vector could be, for example, document this document is based on topic 1 30%, topic 2 50%, topic 3 20%, those kind of vectors. It could be more than 3, but anyway. And based on that, we could sample Z here, which is a topic, right? Yeah, the topic is now, for this document, we're going to get this topic, okay? This topic is yeah, this topic is going to be used. And also this word, okay, to modify my explanation, is instead of document level, it would be more accurate to say as word level. For this word is associated, word in the document. Each word in the document is associated with topic. This topic is now determined, right? And this Y here is basically the metadata information, okay? The metadata information. So what this diagram in the left-hand side is doing is this based on m subscript I, which is the background log frequency, okay? We want to figure out the W here. We want to generate it, and right. So this is the generative story basically. W is component is based on the background log frequency, and the log sparse deviation in terms of log frequency for component here, which superscript A, which means the aspect, the latent variable, which is not a topic, and the first eta to the superscript of T is the latent variable accounting for the topic, okay? And in between I is the interaction. So yeah, so based on all these information, we are going to get the W, which is the word, okay? Generated story. And of course, estimation. These eras are based on variant, their corresponding variances. So we are going to estimate, we are going to fit to the best values of this eta component vector and the variance of that component. Component mean is eta, and the variance of the component. In this case, actually, eta is just a component based on variance of them, the components, okay? But to just to clearly explain, in estimation, we are splitting the component into component mean and the variance of the component. Component mean gets single value by MAP, maxima a posteriori, and because of the sparsity constraint, and for the variance, we use the Bayesian inference because we don't have such constraint, sparsity constraint. Thank you.